The pepperoni.
Pepperonis. I love the pepperonis.
Pepperoni
You
is a
want a
winner.
piece of pizza,
That's
Bill?
always about it.
Sure, I'll take a piece.
Yeah, maybe I will have another one.
Hey Chad, did Doug then pay out on that steak? Wasn't that
It was supposed to be a steak. We've never finished that one out.
Pay 2 Bitcoin instead.
Yes, I'll ask for him to pay in Bitcoin. I'll have to figure out my password to my wallet.
Yeah, so I asked a few folks what I should ask you
Oh.
when they found out you're coming on, and I figured it'd be something about software.
Yeah.
They said actually the favorite thing that Richard talks about is your deep dives in tech stuff,
Oh.
like
The geek outs.
yeah, the solar, the space things, data center shenanigans. So the only thing that I've heard recently that I want to know more about is plug-in solar or balcony solar.
Oh, yeah.
So have you done any kind of deep dive in?
I have not.
the
I mean,
opinions?
the solar shows we did a while ago, obviously the tech continues to advance. What's really happened is that we've gotten some fairly efficient mechanisms for safety around power. Because normally you would never plug a circuit into a live circuit, right?
Right. I'm so confused how they managed to get that to work without burning everything down.
Yeah, and it's because
Does seem like a bad idea.
yeah, on the
Right.
feed side, you have a lot of intelligence, right?
Right.
So it can monitor what's going on, synchronize the waveforms properly. I mean, the nice thing about solar, unlike virtually any other power generation of any kind, is it's naturally DC,
Right.
Right? And so it's not that hard to turn it into the right AC waveform and add supply.
Kind of sneak it in with
Yeah.
what's already in the house.
And you can also make it smart enough to say, I'll only do a dead line, right? So if the power's out, it kicks in, and as soon as the power comes back, it shuts itself off. And again, we have such good control hardware now that that's a lot easier to do than it used to be.
Right.
But generally speaking, native solar is about 400 volts. Like that's what it normally operates at. That's what the cells are designed for. And so the step down is a bit of complexity. It's very much one way, right? Which is why on the geekouts we've done about solar, and I've talked about this fact that buyback is largely wasted power.
Sure.
Right, that your local power industry doesn't want to do that. They're mandated to by the government, and so that's why they do such strict control on it. And it's only getting stricter because for the most part, the power just doesn't flow both ways. It's not water,
Right.
and the transformers aren't set up to do that, and so it's very hard to redistribute electricity. And that's true for these things too. They're not very efficient.
Right.
That they, at short ranges for certain things, they can be made to work. And the main thing is that you can have some power when you don't have power, and maybe make a difference on some costs. The thing that hurts you when you're talking about electricity for most homes is things like air conditioning.
Right.
Well, those run in several thousands worth of watts. Well, that's square meters of solar panel. You're not going to do that.
Right.
So, what are you actually going to get from all of this? In terms of benefit. And same thing with once you get down to those voltages, it's hard to go back up. So, you're kind of constrained as to what they can really do there. Better to spend on batteries. And you're seeing more and more really house-friendly battery designs.
Sure.
Something that'll sit nicely on the fridge, and then the fridge is plugged into it and it's looped in.
Yeah.
And so, as you get into more places that have power by the hour, where there are peak rates around dinner time when everybody's consuming electricity, and your battery's smart enough to go, oh, this is the perfect time for us to just run on battery for the next hour.
Right.
Because it'll save some real money. That I think is a better use of people's money at this point. The batteries are getting cheaper, the electronics are getting smarter. We're getting more arbitrage style pricing, and so you can start to offset all of those things.
That makes sense.
You can get more value than a plug-in solar
Yeah.
for that.
I see all kinds of like off-grid camper van things. Everyone's got their massive battery bank, and
Yeah.
they'll plug it in the panel. And I've seen some videos of people doing that where they plop one under their desk, and they're like, "Oh, it's on a panel outside, and it's feeding my entire workstation."
Yeah.
It's still plugged in the wall, so if it's cloudy out or they've been juiced
Yeah,
for
then
2
they can
days, it can
stick
still go in.
Yeah, and your MPTT, the controller on that is again so quick and so smart. It can change modes in a cycle, so your computer doesn't even notice.
Yeah.
Right. And so you can get away with that, but you need the roof space. You get about 1,000 watts per square meter on a perfectly clear day directly over the equator, which none of us are ever at. And then from that is the efficiency of the panel itself. And for the most part, the inexpensive panels are like 22%. So you're down to 200 watts. and some but less than that per square meter. And so most of your panels are 2 square meters or so. So, make somewhere in the neighborhood of 300 to 400 watts per. You put an inverter on each one so that you can control it individually. If they're tied together, if one panel has a problem, the other panel has the same problem. So they isolate them all, and then you bring them in. You stuff them through batteries, and now because of the maturation of the LiPo battery technology and things, we got a lot more flexibility. The batteries are smaller and denser. What we used to consider a car battery, 12 volts at 40 amps. That same form factor in a LiPo battery is now a 24 volt, 80 amp. Right? It just packs a lot of power. And it's got a lot of lifespan on it as well. Natural discharge cycles on those things is about 6 to 8 hours. And so you can run a lot of stuff, off of that. If you're going to stay on the off-grid stuff, you get away from 120. There's just no need for it. Especially when you think about all of our electronics don't run on it anyway. Right? So it's more complicated, but it's well worth for getting value from it. Just figure out, use what's called buck converters to actually take the base power, which will be 2448, and then step it to the exact voltage and connector for the devices you have. And now you're not wasting all that power conversion to AC and back again when you go into the devices. But you spend time on that. It's not rocket science, especially with an LLM sitting beside you. Like, use your ChatGPT to talk through some of that stuff, and they're going to point you at all this hardware you didn't know about that's designed for those problems.
Sure.
And you can do a lot and get a lot of efficiency, a lot more efficient than you would on the brute force solution.
Yeah.
You almost have to rewiring your house though, right? At the same time.
Pretty much, yeah. I mean, and we probably should have a while ago. I did geek outs on this because the only things that want 120 really are heating coils and motors, right? Anything with a fan, anything with a pump, anything with a heating coil, that wants 120. Everything else is going through a switching power supply down to 6, 9, 12, 18, 20, 24. Like somewhere in that range. And so, we've pretty much got this nailed with USB-C PD, where off of a USB-C cable, your device can now talk and negotiate up to about 200 watts worth of power, but it's trapped at 5 volts. Right? If we took that same technology in a module that would allow us to step up to as high as 24, if you could vary the voltage and the amperage for those things, then you would have a set of plugs in your house that were all natively DC and adjustable. And now you'd have battery packs that aren't rectifying to AC, and you'd have naturally DC solar panels feeding those battery packs in the first place. We just would be wasting a lot less power from that.
Sure.
I switched the whole basement over to LED lighting when we had a flood in the old house. We had the walls off. We had a bunch of things to do, and I'm like, well, I'm just going to go native DC all the way. And the company's called Lumen Cache, and I was far enough ahead that I actually had to become a dealer.
Really?
So I took the certification. Then I paid my electrician to also get the certification, but he never really understood it, so I ended up doing all the diagnostics. But this was just native DC lighting. And here's the thing that happens with LED lighting when it's native DC. It's about the third of the power. So where we were doing 120 conversion LEDs, and they were about 9 watts. Now we're getting the same amount of brightness on at 3 watts. But the dimming is absolutely smooth.
Oh.
When you try and dim, knowing that LEDs are natively DC,
Yeah.
but your light switch is AC. And the way that you dim an AC light, you cut gaps in the waveform. And that's really hard on the rectifier to feed the DC. When you're natively DC, you're either varying the voltage or you're varying the current.
Yep.
And literally, they make LEDs either way.
They support either.
Yeah, they're constant current or they're constant voltage.
Yep.
And then you just adjust that. There is no steps to the dimming. It's just any fraction you want to move to, it's going to move to.
So just
And the lights are under no stress. So the bulbs are 50,000 hours, like 10 years. So I built that out, and so I built it out in 2015. Sold the house in 2022. Hadn't changed the light bulb, and they haven't changed anything since. They just don't wear out.
Yep.
And so it's very beautiful light. And my wife was smitten when we were doing the reno with square pot light, which is really dumb, right? Because the lights aren't square. Right? Like it made no sense. Why do you want square pot lights? You want square pot lights. And I was outnumbered 1-to-1. Like, so what are you gonna do? But I found these LED ones that really were square. They were the strip light, but they literally were wrapped around a piece of plexiglass that was square. So the whole piece of plexiglass lit up completely evenly, and they were barely thicker than the drywall. So I was able to sneak these, what looked like pot lights, into a drop with a vent behind it because it was so thin. And I put too many in because she just wanted them all lined up. And so I think there was like 30 of them in this room. You don't turn all of those on at the same time. Like you'll see the future. It's a lot of light. But I had them in different banks, but you usually ran out at about 30%. And then there were some wall washers, some center fill. Like it was really nice light. And they were color tuned. So I think, as we get further down that DC lighting path, you're going to be able to set that color frequency and the brightness and so forth on any light discreetly, and possibly even be RGB. It's just not that hard now, and be much prettier light that consumes just a minuscule amount of power. But getting it to be native in a house, to have a DC subsystem that takes solar, that provides whole house battery, that you probably do preferential battery for the DC related stuff, which is going to be all your electronics, and then you have an AC bus that's purely for your motors and your heating coils, right? That's what you need it for. You're gonna need one for your refrigerator. You're definitely gonna need one for your stove, and
Washer dryer.
yeah, wash dryer. And that's about it.
Your big appliances. Yeah.
Yeah.
That'd be really cool. One thing you mentioned geek outs.
Mm-hmm.
What's the one geek out you wish you could do, but you haven't ever able to do?
So, I'm an obsessive note taker.
Oh.
Right? I maintain a OneNote list of all the geek outs. I have all the original scripts and things like that. And so I'm always working on shows.
Yep.
And every time a news story comes by, I just have a category for it and I add that new note into it. And every so often, as the list got to a certain size, you can cut a geek out from it. So, wow, you want to talk about weird ones? I've been working on notes for metamaterials for a long time. I've been studying deep sea mining, the nodule mining, which just got some new research on that probably makes it really a bad idea to touch any of that stuff. I have one of my favorite collections is How Cities Die.
Oh.
I'm an archaeological buff. I love history, and I've been to a lot of city ruins and things like that. And you always wonder, like, how did it get to this point? Like, what did that happen? Or you go to a place, like Jerusalem, where there's like 9 cities stacked on top of each other. Right? I even went to what they normally call Troy in Turkey, right? And there's 10 cities stacked one on top of each other in the archaeological mound. The Homer's Troy is like number 7, right? But they built several others after that, right? So some of them are like almost, the oldest ones are almost Stone Age. The last are Greek or Roman. And the 2 cities that have been closest to death in modern history, to me, watching around the world, one is New Orleans, right? With the impacts of Katrina and parts of that Ninth Ward have never been restored, and you just have to wonder, if we had another hurricane of that caliber, like how many people left after Katrina and just never come back, right? The equivalent of this in Texas is Galveston. Galveston used to be the big city, and then it got annihilated by a hurricane in the 30s before we had satellites and things, and a lot of people died. The survivors moved to Houston, and they just did not go back. And Galveston's never been the same. And so, New Orleans sort of sits in that balance as well. And it only would take so many more hits before you have to really wonder whether it would make any sense anymore. The other one that I watch closely is Christchurch, New Zealand. Because Christchurch had 2 really serious earthquakes about a year apart. And it shattered the bedrock under parts of the city. And land that was suburbs was just no longer viable. The house may have survived, but it just started sinking. And so they froze all restoration. It took them several years to negotiate through what was the right thing to do. They called it redlining. So people were forced to move out. So I had a friend who lived there, and her company moved her up to Auckland, and she just stayed there for a while. And she'd actually ultimately never went back. When they finally redlined these neighborhoods, they paid all the homeowners the value of their home the day before the earthquake, which is a lot of money.
Yeah.
But we have this responsibility when a city declares like you can build here, they've validated that land, and more we're running into situations where that's just not the case anymore. And how do you rectify that? What do you do? And it's part of the collective good. The house is the most expensive investment most people ever make. You can't just take it from people that way. You have to make it right. And that whole mechanism of just how a culture breaks down and ultimately people just have to move away. I just think it's fascinating stuff, and it's like we think that's all historical, So when I could see pieces of it and say, like, this might be something that's going to happen again in our lifetime,
Yep.
that a city would just ultimately be abandoned for a variety of reasons and fall into disrepair. I mean, Pripyat, Chernobyl,
Yep.
you know, abandoned for a very good
Yeah,
reason.
for a good reason.
And still dangerous
Yeah,
to this day,
I don't
right?
wanna be
And
there.
No, the Russians took it over during the war, and some overkeener captain decided to get these soldiers to dig slit trenches and killed them all. You know, the ground is still that radioactive. So I mean, it does happen. I collect the notes, and then over time, you know, a story emerges, right? Sometimes you just have to put enough of the pieces together and read it and think about it. Say, like, how would you tell this? You know, How Cities Die is not a finished story yet. Geek-outs are like that. You know, there's a point where you suddenly realize, oh, there's a whole narrative here now. There's something to tell, and then you sit down and really write, like really organize your thoughts. And sometimes they grow bigger. When I went down the fusion path, I didn't think I'd make 3 hours on fusion. It was an accident. But it's stratified. It's sorted into categories, and that it made sense to tell them in 3 separate pieces.
Do you ever ask him kind of one about that? Where you just mentioned, do you think we'll ever have fusion?
It's there's a lot of people saying we're closer than ever, and that's not really saying much of anything because we've never actually been close.
Yeah.
I mean, I'm very excited about what's happening at Commonwealth Fusion because they're using Rebco superconductive magnets, which are the issue here is you don't have gravity to keep the reaction going because if you did, you'd destroy the planet, and then that would be bad. So,
But we'd have fusion.
yes, you would, but nothing else. So we use magnetic bottling, right? We turn the working fluid, the hydrogen to plasma, and then we use magnetic fields to compress it. So the strength of the magnetic field matters a lot. And we have made toroids like the Joint European Torus, where it's literally just copper windings cooled by water to make the magnetic field. And those are fairly limited, one or two Teslas. When you get to the first generation of superconductor stuff like they used for the Large Hadron Collider, so niobium, tin, cooled liquid helium, difficult stuff to work with. In fact, they had a quenching event right at the beginning of Large Hadron Collider, lost 3,000 metric tons of helium in the process, and just about blew everything apart. Like, don't mess with liquid helium, it's dangerous. But you get that thing super cooled down, and now you're talking about 5, 6, 7 Teslas of field. Like, it's much more powerful. Well, Rebcos are these rare earth barium cupric oxides. They're ceramic, and you've seen pictures of them. You remember when we had those little petri dishes with the cube that was just sort of floating there spinning?
Yeah.
That was a Rebco, and that's from like the late 80s. We sort of discovered this particular combination of ceramics that cooled by liquid nitrogen became superconductive. I mean, we've learned a lot more about superconduction in the intervening time. We sort of recognize it now as a state of matter. It's sort of a combination of a compound under a certain amount of pressure at a certain temperature has these special effects. The downside to a Rebco is that it is a ceramic, it's not a metal. So making it into a wire is tricky. Like, it's just not a thing it would normally do. And it took you figured out the science, now figure out the engineering. Like, how do I make this into a winding, into a coil?
Yeah.
And they eventually learned to make it into a thin substrate on Mylar that was sort of a flexible tape, and they could wind that. And so what Commonwealth Fusion did was actually start to build out a toroid in conjunction with MIT, cooled by liquid nitrogen, with a much 15 Tesla field, like much more powerful field. And there's been experiments with these fields before. You may have seen this. You've ever seen the video of a frog just sort of floating in a tube? And that is a Rebco coil, powerful enough that it is lifting the frog with its hemoglobin. The amount of iron in its hemoglobin is enough to keep the frog floating in air. So when we get to these monster strength fields, now you might be able to contain the plasma tightly enough to keep the fusion running for some extended period of time. We still got to figure out how to extract energy
Yeah, I was
from
gonna
it.
say how we do for.
Then you boil water.
Do you boil water with it? Like, it makes you sad. Doesn't that make you sad? Now, I mean, you can. The series is a few years old now, but so the first set I did was the Large Science Project Fusion Project. So that's ITER and Lawrence Livermore's inertial confinement fusion. Like, those are sort of the classics, taught the fundamentals of fusion. The second show I did was like the tech billionaire fusions, all the weird ones. There's the guys who have a spinning globe of lead that they're doing compression on, and Jeff Bezos kicked in his money. And One of the ones that I did in that group was Tri-Alpha Energy. They're still going. They do a kind of pinch fusion where they build up two spheres of plasma in a tube, and then they use magnetic fields to compress those two plasma fields into a narrow spot in the tube, create this fusion pulse, and the pulse creates a really powerful magnetic field that pushes back out, and they collect the energy off that pulse from the windings that compressed it in the first place. So it's literally this alternation of pour energy in, energy bursts
Backs
out,
out.
and pour energy in, energy bursts out. Cool, right? Like I'm not boiling water.
Yeah.
Like ta-da! The largest problem right now is that we need the kind of fusion that you're doing in that scenario. The sort of lowest temperature fusion we can do is DT fusion, deuterium tritium fusion. So these are isotopes of hydrogen. Normally, hydrogen is just a proton and electron, and then when you turn it into plasma, the electron takes a hike, and so it's just a proton. Deuterium has a neutron attached to it as well. This is heavy water, right? It's normally occurring in the ocean. It's rare, but it's not incredibly rare. It's a stable thing. It's a hydrogen atom with a neutron attached. It's heavier. Tritium is its radioactive cousin with two neutrons. And it's got a half-life of about 28 days. So on average, any given atom in 28 days is going to kick off one of those neutrons. It's a natural byproduct of fission reactions. Most reactors emit a certain amount of it, and it's very important in nuclear weapons. It is a neutron accelerator. You use that to provide additional neutrons at the moment of fission. And it's rare, and it's expensive. It's only made in certain ways, and it doesn't last. And so you're going to need a lot of it to run a fusion reactor, DT fusion. So you've got to come up with a mechanism for making tritium, and that requires a lot of energy, arguably more than you're going to make from the reaction. And that's not the only problem. DT fusion also emits a lot of neutrons, and neutrons don't stay in the magnetic bottle because they're not magnetically sensitive, and so they damage the inside of the vessel while that vessel's operating. They talk about in the joint European torus, which they did a lot of runs on from the 90s onward. The inside lining of the torus is made of magnesium, and over time the neutrons were literally powdering the inside. You have to reclad the entire torus over time. So it would be in our best interest if we really want long-running fusion to use anisotropic fusion, so fusion where there are no excess neutrons emitted. And that would be like a proton-boron fusion. So then you're turning boron into a plasma, which is hard. Now it's not 10 million degrees, it's 100 million degrees. But if you get that to fuse, you emit a lot of energy, you don't emit neutrons, and the product's easier to come by. So we're in this race here where, we're getting close to being able to contain that amount of energy long enough to get some chain of diffusion energy from it. We're still struggling. They talk about getting to a Q of 1. And Lawrence Livermore Labs had a moment. This is inertial confined fusion. So they take this really very large laser. They split the beam up 144 ways and then time the raceways for each of those beams so they simultaneously land on a holorum on a central point, which is a little chunk of gold stuffed full of deuterium and tritium. And they had they vaporized that thing. It created a fusion moment. It actually emitted more energy than the amount of energy that was poured into the holorum. So that was a positive Q. First time ever happened. It was a Q. It was like 1.2, something like that. Now it wasn't the total amount of energy used to run the reaction because lasers are not that efficient. So they used a huge amount of power to make the lasers that powerful. It was more energy than the laser that reached the target, but no more than there was used. So it's still in the negatives by a long way.
Okay.
And believe me, we're not looking for a Q of 2. Like we're looking for a Q of 50. Because with all the conversions and things, like it takes a lot to make that make sense. So getting fusion all the way there is bigger magnetic balls than we've ever made before, more powerful ones, stronger ones. Coming up with an anisotropic fuel that we can reliably produce is not too costly to operate and maintain the infrastructure. It's a hard problem. And even then, it's not going to be free power, right? Like running the infrastructure is still going to cost you 5 to 10 cents a kilowatt hour. So, but it's clean. it's relatively cheap. It hasn't got much, depending on the consumable, right? If you have to keep getting tritium, that's a problem.
What's more likely, fusion or self-driving car? Let's keep going down this track.
Yeah, God, you're gonna torture me on that one. I think I mean, we're talking true commercial, profitable, long duration fusion. I think that's further away than
Okay.
a self-driving car. Any kind of we do fusion all the time. It's just like fusion that's in the third version of the story of the fusion series. If you ever get a chance to listen to it, I open that story with muon catalyzed fusion. And Carl does the best everyman ever. He's like, well, what the heck is muon catalyzed fusion? So a muon is a heavy electron. It's a rare, most different subatomic elements actually have 3 states, and electrons are like this too. There's the electron, is the muon, and the tau. And a muon is this heavy form of the electron. It's about 135 times heavier than an electron. It's still an electron, it's not big.
Yeah. I mean, how much does that weigh compared to my pizza?
Yeah, your pizza is going to have far more calories. But if you make hydrogen atoms with muons as their electron body, the mass of the muon changes the shape of the way the hydrogen binds together, and so it takes a lot less energy to cause fusion to occur. And so muon catalyzed fusion is just, hey, we use muons instead to do rapid fusion of hydrogen into helium and emit the energy from it, which sounds really great.
But how do you make?
That's the question.
Yeah,
You need a huge amount of
Okay,
energy to
that's
make
what it was
muons. Right? So it's totally net power negative. Like fusion's not the problem. Energy efficient fusion is the problem. And so there are many ways to fuse these things. And we actually went down the whole low energy fusion path in that one, the sort of so-called cold fusion, right? Which there's some real science in there. Like a lot of dumb things happen. I do the history lesson as well as, what's the science, what do we really understand in that space? But it's hard to be efficient with all those things. So both full self-driving cars and fusion need new science to be practical products. Yeah. So it's a really new science you can't schedule. It doesn't work that way. You have to find it.
Yeah. All right. Next one. What's harder, going to the moon or one of those two?
Well, the moon's much easier. We actually know what we're doing there, and there's a reasonable case for us getting back there. The current wave of missions that are coming along are very much about doing science on the moon, not just the space race kind of we're better than the other guy thing. Although they're trying to make a competition with China, except China doesn't seem to care in the least. And Xi, for better or worse, has a desire to put China on the moon and to have people there, and he's just spending the money to do it for as long as he has that money. China has their own sets of problems. I did a geek out on building bases on the moon back in 2017, based on a European agency space paper, and they very much talked about it in the context of like Antarctica, where you would deploy a set of scientists to a habitat on the south pole of the moon. There's a bunch of advantages of being there, although it's difficult to get there. And they would stay for 42 days. So that's a 14-day day cycle, 14-day night cycle, 14 days day cycle. And then they would leave again. And there's a set of experiments that are uniquely moonish. There's a bunch of things we can learn from operating on the moon for extended periods of time. And depending on who you talk to in this space, there's this whole concept that the moon is the perfect playground for learning how to be a space-faring civilization, for how to utilize resources in place and how to build under different conditions. It's enough Earth-like that it's not that hard to keep humans alive there, but enough different that we have to learn a bunch of things to make that feasible. And we did it in the 60s by spending a tremendous amount of money. The current budget of NASA is 0.5% of GDP, and during the Apollo missions, it was 5%. It was 10 times. Right? That's why they were able to do it. And at the moment they achieved the goal, and Nixon several times wanted to shut down the project. As soon as Apollo 8 happened and they flew around the moon and back again, something the Soviets hadn't done, there was a case where we should stop. We've now beaten the Soviets. Like, good enough, let's stop. But Kennedy had died, and he had said, we're gonna put a man on the moon and send him safely back again. So okay, up to Apollo 11, They barely make it. They almost botched the landing. They were just about out of fuel. They damaged a leg. If they'd been tilted too far, they wouldn't have been able to realign. There was no method for rescue. Like, this was really dangerous, but they pulled it off. Now you should stop. Like, it's just crazy to keep going. It's so darn dangerous.
But they did.
They kept going for a little bit longer. So then they did 12.
Yeah.
Then they had the accident with 13 and very nearly lost the whole
Tom
crew.
Hanks almost lost him.
He
Think
just
what would have
barely
happened.
made it, right? And a great triumph of NASA to get those guys back successfully. I really liked the HBO Earth to the Moon version of Apollo 13 because unlike the Ron Howard, Tom Hanks version where you were with the astronauts, the Earth to the Moon version, you're with the families. And the moment that explosion happened, there were no more cameras. So it's just 3 little voices out in space trying to find their way back home. It's way powerful way to tell that story.
Also with Tom Hanks, though.
And of course, Tom Hanks. Yeah.
Was he in it?
Well, he narrates and opens from
Yeah.
there.
Oh, does he
So,
really?
yeah.
Oh, okay.
Yeah.
That's a great
yeah.
miniseries.
Yeah.
Yeah.
I'll watch that.
So then you get to the J mission, so 14, 15, 16, 17. And now they get the rover, and they now last for several days. Like, they really stretched the potential of the machine. They had a plan out to 20, but they canceled those other ones. And of course, the most important thing in my mind was that on 17, we got our first scientist. You know, everybody else that stepped on the moon was test pilot.
Yep.
And test pilots think one thing, which is don't screw up, don't screw up, don't screw up, don't screw up. But Jack Schmidt was this geologist. He was a real, and he's a geologist. Like, whenever I tell this story for Geek Out or anything like that, I show clips of Jack. Jack was the guy who kept lifting up his visor because he's a geologist. He wants to look at the rocks. And this gold visor, the thing that protects your eyes from being burned out of your skull by the sun, it changes the colors of the rocks. And the rocks are more important to Jack, right? So he keeps flipping up his visor to look at the rocks. And you can hear Capcom saying, you know, Jack, when you get a set, would you put your visor down? They left out that you dumbass part, but it's basically the truth. But that's how important the rocks were to Jack, right? And Jack was like tearing pages off his arm and stuffing it in his helmet to create shade so he could look at the rocks better. And he found better rocks. Like, he knew what he was doing. Like, you know, the reality is that science isn't done by Eureka, found it. You know, science is done by, well, what the heck is that? And that's what Jack was able to do. He found these pieces of unshocked olivine, sort of proved a bunch of core geological science on the moon. We put one scientist once on the moon for 3 days, and he rocked it. Like, can you imagine what would happen if we had 4 of them up there for a month? Like that, there's so much to learn. And that, that's what we're in front of right now. You know, barring all the political dumbness and other things that are going on in space, if you just look at the science of that was one scientist once, and then they shut that program down. And I don't disagree with them shutting it down. It was very dangerous.
Yeah.
The chance of a fatality was almost inevitable. Not that we didn't have fatalities, but we managed to keep all those bodies on the Earth. To have left bodies on the moon would be hard on everyone. Yeah. So I'm glad it worked out the way it did. But we can go back. We've got the tech now. And we have, it's reasonable. It doesn't have to be a 5% all-out effort. It can be a reasonably priced, careful effort. In fact, we're spending money somewhat foolishly even now for various political reasons, not science reasons. And there's a lot to learn. You know, we get that worked out. It's powerful stuff.
That's really cool. One last, at least, question I have. This is more, sorry, we've barely touched software at all, which I kind
That's what I
of,
said we were going to do.
You warned
I
me.
said we were going to do that.
yeah. Like, you definitely, you have your, AI, talk.
Yeah.
And I think that's obviously, it's almost impossible to have a conversation in technology right now without talking about
It's
it.
overwhelming.
It is. Where do you think are the big next hard problems for us to be solving in software going forward for the next few years?
Well, the role of LLMs in software is still very much to be defined. You know, the software development industry is responding to LLMs better than almost anybody else. And I think partly it's because we use simplified language like programming languages that these tools do better with. But even product manager language, like the kind of language you use to communicate with developers, is a narrowed language. And so that works too. Plus, we already have cycles around how we test and iterate and evaluate that allow us to manage the vagaries of the LLMs better than most. I think the big wave that's going to happen for it, well, first off, as the as the excess money comes out of the system when we actually have to be more efficient, this building giant model thing has got to stop.
Yeah.
And more we're seeing it's apparent we don't need that much model, right? You don't need all of 4chan indexed into your LLM to write C#.
Yeah.
In fact, you'd probably be better off without it. Right?
Probably not helping.
Well, and I can't help but wonder if, especially as software matures, the scope of the LLM gets smaller. Like, I wonder if we won't just start tailoring LLMs to individual projects, and that your interaction for new features in a project will be based on an LLM just tailored to the project, and probably run locally, like less computationally intensive. But how are we going to spread this to the rest of the industry, the rest of the world? How do we get to the same kind of cycles that software people think in for other kinds of workloads? I think we might be uniquely qualified to do that for those that are interested, to kind of take that kind of mindset and say, how do we apply these tools to it? What do the new interfaces look like in that form? And what benefits can we bring to all of that? And they're just tools, right? Like, what's the big next disruptive force? Like, we've got to figure out how to make AR make sense. Like, augmented reality, taking the phone into a new form factor. And it's not going to be games. It's certainly got to be social media. Horizon World told us that just fine. What is the info worker role for augmented reality? What made the personal computer succeed was the spreadsheet, right? It happened, when VisiCalc on the Apple II started it, but let's face it, it was Lotus 123 on the IBM PC that put most of the PCs in offices. Everybody wanted that. The smart piece of ledger paper, that was the thing. So what's the spreadsheet for AR? Like, if I knew the answer to that, I'd be working on it. Like, that's a good one. But I think it's a distillation of the problem. We're ready for a new interface. We've really run the gamut on what the slab of glass will do for us and what the pointer and the keyboard will do for us. But it only makes sense when you can find the spreadsheet for it. You find the spreadsheet for it, it's going to take off. And then we're going to have a lot of work. We're going to disrupt all the models again. And I think the LLMs will have a role to play. Like, that's a good interface for interacting that way. But you need the workload. What's the info worker workload that makes sense for that? And, they're feeling around for it. There's a lot of people trying to solve that. And we keep falling into the creepiness factor, We can get away from that if we focus on real work. In that, you find that you'll disrupt the market again. Like, there's more disruptions to come, without a doubt. We're learning to live with these new ones, and it's a tough time at the moment because there's too much money in it right now, and we're in such early days, we really don't have the picture. But by the time that one settles out, I think we're going to hit with the visor sooner or later. Somebody's going to find this thing we're really going to want. And a bunch of the peripheral sides of it, let's face it, navigation's better through a visor. Communication's better through a visor. Translation's better through a visor. But they're not the keystone product. You don't get the product for those things. You get the product for something more important, and those things come with it. So we got to find them more important.
And right now, unfortunately, probably it's been driven a little bit by, you mentioned the creepiness factor. The social media companies are the ones kind of driving a lot of that.
Social media is creepy from the outset. I own a Google Glass. And when I first took the Google Glass out into the wild, I got the normal reaction for a new technology. Can I try it? That's what everybody wanted to do. I had smartphones before anybody else, and same thing. But I had smartphones before the iPhone had hit, and they were too geeky for most people. They tried for a while, they go, that's just weird. You have a fine time with that, off you go. And when people tried the Google Glass, they were disappointed. It wasn't that good. And then they attacked it. Right? But I remember getting one of those early Samsung phones, post iPhone, and now it was good enough. And you could tell, because when someone played with it, you couldn't get it back from them, right? When the product crosses the line, you'll know. It's apparent. When the visor's good enough, we'll change the social construct around it. It used to be that walking around with a phone was unacceptable.
Or sitting and talking, or if you were at a table doing this.
You would never. But once the phone was good enough, we changed the social construct. Once the visor's good enough, we'll change the social construct. Right? All those protests we're using right now, those is excuses for an inferior product. Once we have a better product, that won't matter. We'll change the rules.
Cool.
Good way to think about it.
Any more questions?
I do, but
I'm going to say one
Next
thing
time.
next time. I really appreciate this one. My wife, I don't think has ever watched one of these episodes.
Yeah.
I'm pretty confident in that statement, actually.
You filmed one in your living room while she was there.
She still didn't watch it. She still didn't watch it. She didn't watch yours, Bill. This one I am going to recommend she watches. You've dropped so many fun conversation points
Yeah.
on us. And she probably, if she'll maybe stop once the moment we hear the word AI.
Yeah.
That will be the moment she checks out, but
That's
this
fine.
was excellent.
I appreciate it. I had a good time.
Thank you.
Great pizza.
Good.
Yeah. Even though it had cream cheese.
Yeah, that's the safe one, and it wasn't as good as the unsafe one. But they
Yeah.
were both good pizzas.
There's always something to learn.
Yeah.
Yeah. No, I'm not putting cream cheese on my pizza if you're asking. If that's what you're asking. I'm not doing it.
Yet.
Yeah. Next time you come here, stop by again. You'll eat it again.
Okay.
Like third or fourth time, you'll be like, I can't eat pizza without cream cheese.
Yeah,
Then we get this brisket.
That's just weird.
Yeah.
No, I want the spicy one, I think.
Okay,
I'll
well,
try that
The
one.
Randy Ross.
Randy Ross,
We'll
yeah.
do that
Randy
one and the
Ross.
barbecue brisket.
Okay.
Yeah.
I like that plan.
Yeah.
Okay. Well, if you've got opinions on Fusion, full self-driving, AR, or cream cheese on pizza, go ahead and leave a comment down below. Like and subscribe if you like the content. Richard, thanks for coming out.
Yeah,
My pleasure.
Tune in next week when we eat more cream cheese on pizza, obviously.
I was just in Madison when they announced the relocation of the manufacturing facility for Rialto, the magnetic mirror fusion.
Oh, yeah.
And I don't know enough about magnetic mirror fusion to understand why they believe this is actually the thing that's gonna work.
I don't know why they do either, right? It's just another way to do confinement,
Yeah.
right? The toroids dominate because plasmas like toroids. Like it's a natural form that it twists into. There's another kind of fusion reactor called a stellarator. But there's a big one, the Max X in Germany, and where literally the construct of it is the twist that a fusion plasma tends to form into. So it's literally they've built the thing to be in the shape that field wants to be in. A lot of these magnetic confinements, they're really trying to force the plasma into an unnatural shape, which should increase rate, but it's just harder to contain. On the other hand, making a donut-shaped magnet is hard too, right? There's a lot of different layers of the way that containment has to work, and it's hard to keep it contained. So, I mean, I'm not going to reject any given method. Like, you want to be weirded out, look at what General Fusion is doing with their spinning ball of lead. Like, it's bizarre. But why would you discount any idea? They all not work about the same, right?
They're all failing.
Yeah, everything's failed so far. Try everything.
Yeah. And then you didn't say quantum.
I did not. I have opinions,
I know.
Ooh.
but
I want your opinions.
yeah. A quantum computer is not a general purpose computer. It is a supercomputer. It's a specialized class workload. I mean, it'll make a lot of sense to have those machines in the cloud when they are actually viable machines. They do certain classes of supercomputing workload that are potentially valuable. The whole Shor's algorithm breaching of encryption is stupid. Yes, eventually we will build machines with enough bits in them that they have the possibility to decrypt large prime key encryptions. We also don't have to use prime keys for encryption. In fact, we're moving away from it now, right? We're going to lattice encryptions and things like that on the possibility that at some point there will be a quantum computer that is actually able to break prime-related keys. We just use them because they're easy. The computers are good at generating them, but it's not the only way. So just move off of that style of encryption. You're going to have that before we have the quantum computer now, because the NIST is sort of pushed on it, and the big cloud vendors are going, okay, all the browsers are going to have it, and all of the app services and things will have it. You can just switch to it whenever you want. That's a red herring. By far, to me, the most important thing you'll do with quantum computing is quantum chemistry problems. As soon as you get to a certain number of electrons involved in interaction, classic computing just breaks down. It can't handle them. And there's a ton of known problems that we just can't work. My favorite one is the nitrogenase problem. So this is an enzyme that affixes nitrogen to hydrogen at low energies, at chemical energy levels. We can do it with the Haber-Bosch process, but that's huge amounts of energy, right? It's making fertilizer and explosives, but whatever.
Yeah.
It's like 1% of all the power consumption on the planet is doing that, right? This hugely energetic process. And here we have this enzyme that does it inside of a bean rhizome, right? This is where crop rotation comes from. Like we learned 9,000 years ago, we learned if you keep growing wheat over and over again, the soil becomes depleted and the wheat won't grow. But if you rotate in other crops, and particularly rotate in a legume like a bean, the soil rejuvenates. You harvest the beans off, like you take the food, but then you plow the plant under, and then you let it sit for a year in decay, and the soil's pretty good again. You can grow wheat again. And we improved the rotation by like rotating in animal crops and cover crops and things like that, so the animals would then eat it and add their fertilizers to it. Like we got better at doing this rotation until we started making fertilizers, and now you can just keep soaking the ground with more chemicals, which has its own consequences, but it lets you stick with your monoculture if you're happy that way. And so we've studied this rhizome on the bean. It's in the roots of the bean that literally does this affixation of nitrogen. And inside this thing is this enzyme that does this reaction. And we've studied it long enough that we know that it's an interaction between a couple of atoms of molybdenum and a couple of atoms of iron that do this catalytic reaction that sticks the nitrogen to the hydrogen. But it's like 135 electrons involved in the interaction, and the classical computer just melts down. But a 200 logical qubit quantum computer ought to be able to solve that, ought to be able to run the math on what that interaction actually looks like. And once you knew what that catalytic reaction was, you'd have a chance of recreating it. Like you still got to do the engineering and try and make it into a product, but now you have a template for how it would work. And that, now you start thinking in terms of, I could have a little stake with maybe a solar panel on it or a watch battery in it that runs this little chemical interaction and puts nutrients directly into the soil of the plant. Right? It would transform the way we could do agriculture. Well, that's one. There's like 200 of these. And they're nowhere near the power level of what we'd need to crack RSA 4K. We're certainly sitting around like 50 entangled qubits at the moment, and we need about 200. But it gets exponentially more difficult to entangle as you go along the way. And if you got there, there's just this battery of things. Techniques are like, we hack batteries, right? We don't actually know how to make a battery. What we do is just mix stuff together and test it. We've got the testing process really fast, but we're just whacking away at the problem. Right? It's too complex a reaction. Well, again, quantum chemistry could actually figure this out. You could make that leap. I'm not going to call it quantum leap. I'm not that cliche. I'm not that guy. I'm not going to do that.
You just did.
Wait, what? But you'd suddenly say, oh, this is the perfect combination. Let's use these compounds. You have this dramatically better battery, right? We've just been iterating on battery chemistry and making incremental improvements, literally just by hacking our way through it. So actually understanding superconductors, seeing, is there a room temperature superconductor out there somewhere? We still have to do the engineering for every one of those things, but that's the set of really useful problems that could be dealt with there. The issue is, to me, quantum computing feels very much like von Neumann computing, traditional general purpose computing, circa like 1948, where nobody has a good bit, right? Maybe you do it in a relay, maybe you got it in a vacuum tube, like you got a lot of different techniques. Everybody's bits are different. Well, that's what quantum computers are right now. Each different organization's got their own form of bit. This guy's doing the fermion bit. This is a Margeron bit. Like they're doing all these different techniques to try and build a qubit. And they're unreliable. They're flaky, weird machines that have to be cooled liquid helium. Like 4 guys in a lab coat. It takes about 6 days to get the machine to temperature before you can do a run for an hour. Then you got to clean the whole mess up and try again, right? But, because I'm the history buff, I know that when William Shockley, who was one of the guys who built the original germanium transistor for Bell Labs, went out on his own, made Shockley, the company. He moved to the Silicon Valley. It's one of the reasons Silicon Valley is the Silicon Valley. He had a contract with the U.S. Air Force to build navigation systems for ICBMs. He had to make the circuitry smaller, right? And so he was working towards the concept of an integrated circuit. He knew that it took layers of doped semiconductors to make a transistor. So what he was trying to do is make sheets of them and actually be able to drill through them to make transistors at density. He was trying to make the first chips. And he used an old electromechanical computer to work out the combination of doping compounds to make the different substrates. And that got him to the ideal bit for a general purpose computer. Without the old unreliable computers, he would have had a really tough time figuring out what it was going to take to make the perfect bit, the one we use today. And it makes me wonder, because, you know, history may not repeat itself, but it does rhyme, that it isn't going to be one of these flaky, liquid helium-soaked chandelier-type machines that has got enough compute power to work out the weird compound we're going to need to make the perfect qubit. And that will then turn the quantum computer into something reliable that can get to these bits where we start making a difference in society. And at that point, I can't even guess what it's going to look like, you know. The Cray 2 supercomputer circa 1985 had about 2 gigaflops of processing power. We modeled nuclear explosions off the back of it. We did the grand transit of all the planets with the satellites and so forth. Today, that's the same computing power in an iPad that you hand to a kid to play Candy Crush. Maybe that'll happen. You know, that we'll end up getting to the point where, yeah, we will have quantum computers. We'll just have them in our iPads. I don't know the answer to that.
Or our glasses.
Yeah, or wearing in our glasses frames. The fun thing about that whole problem space that I just went through is they're all deterministic problems. The real question is, well, how many quantum computers are you going to need? Like, we've got about 200 of those things to work out. Like, what's the non-deterministic problem that quantum computers need, besides breaking encryption? You know, there's not that many of them. It's an odd problem space. But you take out those 200 or so big quantum chemistry problems, you change the world, big time for us. You know, it'd be astonishing. It's not a bad goal. But
All right, so where are you gonna land on the quantum first, self-driving car, fusion? What's the order?
Or cream cheese on pizza.
Yeah, cream
everyone's
cheese.
top 10 ingredients.
yeah, that I actually have to have cream cheese on pizza.
Yeah, which one of those is coming first?
Yeah. And again, it's like, are we going to get to a quantum computer that's out enough entangled qubits that it can, or logical qubits that can actually do some reasonable work? Well, I'll argue it's entirely possible. We're already there. That's just pretty secret right now. There's a lot going on in the space, actually, and they're doing more error correction stuff. So that is further along than you think. I think it'll probably beat self-driving cars in fusion. But the iPad version is probably less likely.
Yeah.
You know, it's going to be a supercomputer. You're going to rent hours on it out of the cloud.
Yeah.
If and when it's the time. You can sort of do that now. It's just not particularly useful.
Very cool.
Thank you so
You
much.
tell I still stories for a living?
Yes, you do.
Oh, you want the quantum star? Well, okay, let's go.
That was amazing.